Welcome everyone, and thank you for joining us today. My name is Dione, and I joined the COMET initiative from DataSite to lead our collaborative efforts to improve PID metadata. I'm joined by my fellow organizers, John and Adam from CDL, Juan Pablo from PKP, who were the original conveners of the task force discussions. And since then, we've expanded to include Maria from DataSite and Nees from CWTS. And we're also joined by a talented data scientist, Path. I would like to hand over to Nees to share a bit about his perspective, or the CWTS perspective, on joining the COMET initiative.
Yes, thanks, Dione. Well, my name is Nees van Eck. I'm a researcher at the Center for Science and Technology Studies, CWTS, at Leiden University. And I'm very pleased that my research center recently joined the COMET Organizing Group alongside CDL, DataSite, and the Public Knowledge Project. And let me indeed briefly explain why we decided to join COMET. Well, at CWTS, we have been at the forefront of scientometrics for more than 4 decades. And in recent years, we have been deeply engaged in a transition towards a new way of doing scientometrics, one that builds on open data. And this is part of a broader transition to openness of research information, a transition we actively support as one of the initiators of the Barcelona Declaration on Open Research Information. And very important at CWTS, we have learned that this transition can be successful only if we are able to demonstrate the capability of open research information infrastructures to outperform traditional proprietary data sources in terms of data quality. And this requires the use of persistent identifiers combined with clever strategies for enriching the associated metadata. Without effective metadata enrichment, the open research information transition is unlikely to be successful. And that's why CWTS believes COMET is so important. We see COMET as a key driver for this transition, enabling collective efforts to ingest, curate, and enrich metadata contributed by a wide range of individuals and organizations. And this work strengthens the quality, the connectivity, and also the trustworthiness of open research information. And this has direct impact on the use of open research information to make research outputs discoverable, to advanced responsible approaches to research assessment, to monitor the growing adoption of open science practices, and to support better decision-making in the research system. And for all those use cases, having high-quality metadata is really, really critical. And that is why we, as CWTS, joined COMET. So back to you, Dione.
Thanks very much, Nees. For those of you new to COMET, let me quickly recap our journey so far. The conversations on community enrichment were reignited at the Force 11 and the Paris conferences on open research, leading to a call for participation with a very high response rate. Over 80 individuals participated in the task force phase, which included listening sessions focused on the challenges, needs, and the use cases for improving PID metadata. The community defined core requirements and governance considerations for this shared metadata enrichment plan. And this task force phase culminated in a call to action, where we received expressions of interest to contribute effort and resources. This enabled us to establish structures and to begin planning the pilot projects which we're sharing with you today. Before addressing solutions, it's important to acknowledge the immense value that the PID metadata system already provides. Persistent identifiers and their metadata form the core of our research infrastructure. They provide an authoritative source of truth for identifying, discovering, and tracking research outputs across many different stakeholders, including researchers, funders, institutions, and the broader community at large. Whilst this ecosystem has flourished, we're now encountering some real limitations. The main issue is that the current system for maintaining and enriching PID metadata is inefficient and disconnected. And these challenges are multifaceted. Due to the complex pathways of metadata production, there's created a significant barrier to corrections, leading to a growing debt that creates a paralysis and discourages improvements in a self-reinforcing cycle. Because stakeholders develop correction mechanisms outside of the PID ecosystem, this leads to siloed corrections, where there are parallel efforts addressing the immediate needs, but that they unfortunately operate outside of the authoritative sources. We also see a profusion of undocumented and proprietary enrichment systems who lack standardization, which makes it difficult to compare, validate, and integrate improvements. This results in fragmented authority and provenance. Corrections made in one system rarely propagate back to the source. There are conflicting version issues, and without clear provenance, it's difficult to assess their reliability and to determine reconciliation pathways for these improvements. But these challenges are also an opportunity. It's an opportunity to rethink our approach. And that is why we came together as a community so that we can build a shared system to collect, validate, and include the community's enrichment work in PID metadata. Let's go into the model. Here's a proposed new model where the original creator has the necessary authority, but stewardship for metadata quality is shared with the community. Community members can contribute back enrichments to the DOI metadata, and these enrichments follow structured rules, including provenance requirements, so that the community can validate and trust the system. This model requires new infrastructure, but it's infrastructure that complements existing systems. A centralized data store where anyone can contribute suggestions for improving metadata and make those suggestions available for reconciliation with the source records when that's required or desired. The envisioned workflow for this new system includes 5 key stages. At a very high level, we're ingesting enriched metadata, which could come from manually created processes or machine processes. We're validating those submissions and processing them. Naturally, there's going to be a step where we need to review conflicts, and those would be reviewed through community validations. And when we have a set of submissions that are ready to accept, we can publish those enrichments as an enriched version of the metadata record. So that's the vision and the ideas, but how do we get there? In the task force phase, we articulated how to transition to a model with community at its foundation. We said that we needed to move from individual to collective stewardship, from siloed to collective benefits, and to build trust through transparency and governance. Since the task force phase, and now that we've entered a pilot phase, we've expanded this model and we are identifying 6 key elements of the COMET model that provide practical guidelines for our approach. Treating each metadata field as a discrete feature enables incremental progress and focused problem solving. For example, we can address a cascade of problems by focusing on incomplete metadata affiliation specifically. Addressing diverse content types, such as journal articles, preprints, data sets, software, etc., would ensure that we are creating flexible solutions rather than narrow improvements. And engaging a diverse amount of organizations in different regions ensures that solutions address real community needs across different languages, geographies, and resource levels. A primary concern is bringing together high-quality metadata from disconnected systems. For instance, universities invest substantial effort into their CRIS systems with meticulously curated institutional data, but this valuable information remains isolated. And any solution that we're looking at is going to require a way to bring back those improvements to the source. So by creating both direct and indirect integration with DOI registration agencies and platform-mediated integrations through systems such as PK's Open Journal system, we're able to bring back the metadata to the people who need the improvements. And finally, this model aims to unite new and existing enrichment solutions, positioning COMET as a collaborative facilitator that develops new capabilities whilst amplifying existing community solutions. For example, some of the projects that we're focusing on create novel technical approaches using machine learning, for example, while others deliberately build on proven approaches, such as adapting established matching strategies. So let's take a look at these projects specifically. Collectively, the projects aim to demonstrate this COMET model. They also serve to test real-world cases by investigating different approaches to metadata enrichment, to evaluate their effectiveness, their accuracy, their cost, and their scalability. Our goal is to diagnose problems by focusing on high-impact issues so we can quantify the problem across the scholarly record. This phase also further refines COMET's framework for how we engage with the community, how we interact with our advisory group for support, and on a technical level, how we do things like share data. They aim to deliver real, tangible results early on, and of course, they need to inform the future infrastructure needs that we're going to build. Let me walk you through these projects now, looking at them through different lenses of that COMET model. We have 8 projects in total, improving various levels of the metadata. If we consider the concept of fields as features, we have a primary focus on affiliations, which you can see in a number of projects. We are also investigating improvements to resource type, to titles, to funding, and to related identifiers via a matching strategy. Addressing a variety of content types can be approached in a few ways. We are focusing on, first of all, the ability to find different content types through the project of improving resource type classification, as well as improving vague titles that will allow you to find those resources. And then we are looking at 3 separate projects focusing on parsing different content types. So parsing affiliations in preprints, in ETDs, that's electronic thesis dissertations, and journal articles. Each of these having different challenges owing to the tools and practices of these groups. So it's important to look at each type separately. And then finally, we are looking at matching different types of content, preprints to journals. And in our projects with the CRIS systems and funding metadata, we would touch on many different content types. In terms of our progress, I wanted to let you know where we are. First of all, we're tackling a number of projects at the same time, and we already have 1 complete project, which Adam will present today. The project on improving resource type classification is currently in development. And then we have 3 projects, the ones focused on affiliations and parsing. All 3 of those are currently in the phase of creating the benchmarking data so that we can move to development. We're also scoping a few different pathways for leveraging affiliations from CRIS systems with the different pilot participants. And we'll continue to share our progress and our findings for your input and comments, which brings me to the first completed project, which we're going to share with you today. And I hand over to Adam to present that.
Hi, everyone. My name is Adam Buttrick. I'm one of the organizers of COMET. I see lots of folks from the task force phase back again, so thank you so much for joining us. Thank you as well to everyone who's new here, learning about COMET and everything that we're doing. I want to talk to you about some exciting work that we did for our pilot project on preprint matching for arXiv. Okay, so to outline the opportunity here, as hopefully everyone is aware, for over 30 years, arXiv has been this indispensable pillar of the global research community. As a premier venue for preprints for many disciplines, it allows for rapid dissemination of new research, modeling the kinds of open science principles that are now central to research reform movements worldwide. So long before there was open access or open research information, long before these became rallying cries, arXiv was there demonstrating the power of immediate and barrier-free sharing of this work. So then, in thinking about how COMET could add value to arXiv's foundational efforts, one opportunity that presented itself was the chance to strengthen connections between arXiv preprints and the published forms of these works. So since 2022, arXiv has been registering DOIs and DataCite for all of its work, connecting its metadata with a system of broadly scholarly infrastructure. And this integration allows arXiv to not only track and declare relationships between their preprints and published works, but then also broadcast them to all the sources that consume DOI metadata. Next slide, please. And to be clear, these are connections that are already being made. Currently, about half of arXiv records and DataCite link to the published forms of these works. These links are populated through 2 mechanisms. So authors can voluntarily update their arXiv records with the publication links. And then separately, there's an optional data feed process where publishers can assert these relationships as well. So as we might imagine, both of these approaches naturally produce some gaps. Authors don't always return to update their preprints after the works are published, and publisher participation in this feed process is varied. So what we did is some cursory analysis of all the unmatched works in arXiv. And this showed that many of these works that are unmatched actually do have published versions. So it seemed if we were to take a stab at some more proactive automated forms of discovery for these published works, we could actually find and create many of the missing connections. Next slide, please. So to get started on this, we took an approach that embodies the kind of core of the COMET model, leveraging existing high-quality enrichment work being done by the community. So over the years, many preprint matching strategies have been developed and put into use into various services. So what we did is we undertook a review of these through the lens of our own ambitions. What we found is that there was one preprint matching strategy that seemed especially fit for purpose, the search-based matching with validation strategy developed by Crossref. Specifically, this strategy performed exceptionally well at the preprint matching task using an open source, reproducible, and benchmark methodology. This makes it the kind of ideal candidate for extending to our use case. This being said, our specific task, matching arXiv preprints to published works, differed from the strategy in two important ways. First, we need to match in the opposite direction, so from preprints to their publications, rather than from publications back to preprints, which is what happens in that original cross-ref strategy. This inversion also means dealing with input metadata that may be more partial or varied as what accompanies the preprint, often because it becomes more complete and standardized as part of the publication process. Second, we face the additional complexity of bridging the gap between two different DOI providers. So arXiv registers its preprints with DataCite, while the published articles we are targeting are generally registered in Crossref. Each of these providers has distinct metadata schemas with different fields and data structures for describing things like authors, titles, year of publication, etc. But then referring back to the COMET model, these challenges are exactly aligned with our principle. We need to break down metadata silos, we need to build new integration pathways, and we have to work to connect enrichment tools with existing infrastructures. Next slide, please.
Oops, sorry. There we go.
Thank you. So to establish a baseline for repurposing the strategy, we did something fairly straightforward. We updated the logic in the cross-ref strategy to account for the differences between the two schemas, and then just naively inverted the content type queries that are used to do the matches. So match from preprints to published works. We then tested this approach with a benchmark dataset derived from the existing preprint to publication links in arXiv. Those links that I mentioned are created through author updates and the publisher data feeds. This very simple approach demonstrated high precision. When it found a match, it was generally correct, but recall was somewhat low, meaning that it was failing to discover enough of the links between works to make it truly viable. Next slide, please. So this outcome, of course, prompted us to take a deeper look into why this simple form of inversion had failed. What we found is that the metadata in the arXiv records can differ from the published works in ways that affects the strategy's ability to surface the correct candidates for matching. For example, author names and preprints might use abbreviated forms, while published versions include full names. Authors themselves can be added or dropped off between the preprint and publication. Titles can change between submission and publication, becoming more concise or elaborate. And time to publication can occasionally span a wider range than the defaults in the cross-ref strategy assumed. So all of these factors required us to do a bit of refinement to fit this community strategy to our specific task. Next slide, please. So what we did to revise the strategy was to revise the strategy to incorporate some more complex heuristics, as well as make use of a flexible and weighted scoring system for its similarity measures. So what does this mean in practice? For title comparisons, we improved the string normalization to better handle some of the variance we observed. We also used a blended average of a few different string similarity measures instead of just one form of comparison as occurred in the original strategy. This allowed the strategy to better account for title variations, things like words being reordered or text being removed or added. For author comparisons, we implemented a form of pairwise matching that generates and compares multiple variant names, allowing it to handle the differences in formatting we saw between arXiv preprints and their published works. Additionally, we observed that preprints in some fields, like high-energy physics, had very large author lists. So we developed a discrete and more computationally efficient method for comparing just the family names for these large author lists, but which maintains similar accuracy as our pairwise matching. For publication years, what we did is we introduced a graduated scoring mechanism that assigns decreasing weights based on the difference in publication years, acknowledging that while most published works do appear within 3 years of their preprint, which is what the original strategy assumed, some legitimate matches occur outside of this range. And then, as I mentioned, in the final scoring, these field level measures were then reweighted with multipliers shown to identify the best matches. So for these multiplier weights, rather than relying on our intuition or doing a lot of manual fine tuning, what we did to find the optimal configuration was to implement an automated grid search that tested different combinations of them for title and author similarity, publication year gaps, and just more basic thresholds of difference. So what this involved is checking many different parameter combinations against our benchmark dataset, evaluating each configuration's impact on precision and recall. We ultimately then chose those that maximize for our performance metric, which was F0.5, where precision is weighted more highly than recall. Next slide. So the good news here is that all of these refinements proved successful. Testing the revised strategy with our benchmark data set, we were able to achieve about 95 to 96% precision and now 90% on recall. This improved performance would now allow us to capture the majority of connections between arXiv preprints and their published works. So with these results in hand, we did a full run against all arXiv works that currently lack these links to published works and returned over 730,000 new connections, pushing the overall rate of linked works from about 45% to 71%. So 45% is what is currently being asserted, 71% is what can be achieved with matching. Next slide. As a final validation step, we also compared our results against OpenAleX's more strict kind of location matching. So this is what they use to identify when a work exists in different venues like repositories. And it's also where the same kind of links are made between preprints and published works. Here we found that OpenAleX identified about two-thirds of the same connections. This is kind of what we would expect relative to the strategy being far more conservative, but it's also reassuring because it demonstrated that both strategies were converging on similar results. Additionally, we verified that our revised strategy maintained the same precision and recall scores when tested against Crossref's original benchmark dataset, which was found to be true. So we took the strategy, we refined it, and then we refined it back into being able to match the same kind of data that Crossref used and found it performed the same. So there's no regression. So what this confirmed is that we hadn't sacrificed any of the original strategy's general applicability while tailoring it to our specific needs. Next slide, please. Okay, so in terms of next steps, we're currently working with both arXiv and DataCite to integrate these new enriched connections back into arXiv's records, working towards our COMET model goal of round tripping, getting those enrichments back into the source. The full matching result dataset has now also been published on our Zenodo community, which I'll provide a link to in the chat. I think someone might be asking for it already. Oops. Let me remove that one. There we go. We're also exploring to what extent this strategy can be used to match other preprints in DataCite. So there's about, I think, 250,000 other preprints outside of those that are provided by arXiv and DataCite. So can we match these as well with the same strategy, as well as if it's applicable for additional content types where titles are often the same between the published works and the other content types. So we can think of like supplemental works for a publication or a data set that's associated with the publication often share the same titles and authors. So maybe we can leverage this strategy to match those as well. Okay, so that's all from me. I do want to give a special thanks to Dominika Tkaczyk for first developing Crossref's fantastic preprint matching strategy. Couldn't do any of this work if she hadn't done it first. Under her direction, the data science team at Crossref is also doing a bunch of great work on various matching related tasks, which they just outlined in a new blog post. So please make sure to give that a read to kind of understand where we're coming from and what we're building upon. I'm going to put a link to that in the chat as well. I also want to thank Ludo Waltman from the Center for Science and Technology Studies at Leiden University, Nees' colleague, who helps advise on this project. Ludo and his colleague, Katie Corker, also just published a great piece on preprinting and its relationship to the kind of matching that I was just describing on the ASAP Bio blog. So please check that out as well. And I'll throw a link to that in the chat. All right, thanks. So that's all from me. Turn it over to Dione.
Thank you. So now I would like to turn to how everyone can get involved or continue to get involved. We have put in place a governance and participation structure. Our structure aims to balance operational efficiency with community participation through 3 different levels. The organizer group, who is here present today leading this meeting, they are forming strategy and conducting the activity of the pilots and organizing what comes next. Then we have a small group of advisors who are providing strategic guidance. We can provide a link to the advisors on our website. And then, of course, the broader community, everyone that is here and who may not be here today, who are hopefully going to share enrichment data and ideas, who are going to participate in pilots, and who are ultimately going to advocate for COMET and its model and inform their peers and keep everyone updated on what's happening. To get involved on a practical level, you can contact us, me specifically, with any projects that you wish to join or nominate new projects. We've also set up a suggestions board in GitLab, so you can outline specifically how you might want to contribute enrichment data or new approaches to enrichments with us. And then, of course, you can keep following us on our various socials, and Claire will link in the links for us in the chat.